Okay, in Chapter 7, we're going to go ahead and continue talking about the differences between the population and the sample. So the parameters and the statistics. And we can think of the true value of a population parameter as like a bullseye on a target. And so this is our true parameter right here. True parameter right here. And the sample statistic is an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. So our first thing is bias. And bias means that our aim is off. And so we're consistently missing the bullseye in the same direction. Our sample values do not center on the population value. So when we're looking at this, and when we're looking at this, you see how this whole cluster and this whole cluster, they're centered away from the center of the bullseye. So the center of those shots is not the same as the center of the bullseye. And so that means that we have some bias. We also have something called variability. And high variability means that the repeated shots are widely scattered. And so when we're talking about variability, we're looking at our spread. And so when we have high variability, those shots are spread apart. When we have low variability, they're all really consistent or similar or in a nice tight cluster. So here, we're off aim. And scattered. So this has high variability and high bias. And that's what we don't want. We do not want this. It's like the worst of both. On our next example, we have high bias because we're centered away from the center of there, but they're all really close and tightly knit in there. So we have low variability. So low spread, which is good, yay, but high bias, which is bad. Now our idea is that what we really want to have happen is that we want low bias or minimum bias and no or low variability. We want to minimize these as much as we possibly can. So again, this goes back to our chapter 4 information on how to design a study. If we design our study correctly, we should be able to minimize this. And so again, we already talked about this diagram up here, but here, look at our dots. When I look at that dots, they're centered in the right spot. So that means we have good bias, low bias, because we're centered right here, but we still have a lot of spread. Which is bad. So we have high variability. What we really want, again, low bias, low variability, low or no. Now, a statistic is used to estimate a parameter. A statistic used to estimate a parameter is an unbiased estimator. That's a really important term that you need to know. Trust me, it'll be on your test. If the mean of the sampling distribution is equal to the true mean of the population being estimated. So, to get a trustworthy estimate of an unknown population parameter, start by using a statistic that is unbiased estimator. This ensures you won't tend to overestimate or underestimate the value. Unfortunately, using an unbiased estimator does not guarantee that the value of your statistic will be close to the actual parameter, but it does the best job we can with our tools. Now, the variability of the statistic, again, is described by the spread of its sampling distribution. This spread is determined primarily by the size of this random sample. Larger samples give smaller spread. So we want larger samples. And n is our sample size. Want n large. Why? Because that decreases our variability. So if we get to choose, we want more in our sample rather than less. Smaller samples are easier to calculate. Smaller samples are easier to gather. They're less expensive, but then we have higher variability and more issues with that. So we typically want n large so that it'll decrease our variability. Now, keep in mind this is really important. The spread of the sampling distribution is not determined on the size of the population. No, it is, we want the size of the sample. Now we have to be careful because of our independence rule. We need to make sure that our population is at least 10 times larger than our sample. So we want large sample. Again, n. We want a large sample, but we want it less than 10% of population. So that way we can use that independence rule, where we don't have to worry about independence as long as our population is less than 10%, or our sample is less than 10% of the population. Okay, so what we have is we have a population distribution, and we have a sampling distribution. So we took lots of samples from this population here, tons and tons of samples, and then we went ahead and recorded the medians of all those samples over there in our sampling distribution. So what we have is a histogram that shows the intervals in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, our median, so we're not dealing with mean, we're dealing with median, is 75. Now over here in our sampling distribution, we took lots of samples. In fact, we used a software program and we took 500 samples, all of size 10. So n equals 10, because our samples are all size 10, from the population. When we graph that, we see a curve, somewhat, and the mean of this is 73.5. So the mean of all of our median values is 73.5. So the question now is the sample median an unbiased estimator of the population median? So unbiased means that this and this should be the same. So no, it is not unbiased. Since 73.5 is less than our population parameter of 75. It is close, but it is not the same. So it's not a truly unestimated or unbiased estimator. Okay, suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? So remember, we want a larger sample because what does it do? It decreases our variability. It decreases our spread. So the spread will be smaller with a larger sample size. Describe the shape of the sampling distribution. So we're back to our sampling distribution. Let's look at that shape. Obviously skewed. And our tail's over here, so that means it is left skewed. Does that mean that we are overestimating or underestimating the population median? Well, if the true median is 75, which is right about here, look how much more of our data is below the 75 rather than above the 75. That means more and more often we're estimating down here, which is below the true median, rather than above or at. So that means we are going to underestimate the population median. And that's it for today.